Uh, I will also discuss the questions from friction, work by energy, and Newton's laws of motion from the major test number 5 that was concluded last weekend. And I'll just take you through those questions. If there are any doubts, we can discuss the questions in which you have any doubts. So just give me a moment. I will share the question set from the major test 5. Okay, so as I said, I'm going through the question bank from the major test, which was related to work energy, friction, and Newton's laws of motion, that part of the question bank. So please go through these questions one by one and ask me over the text if you have any doubts in any of them. So let's start with question number 1 or 2. If anybody has a doubt in question 1 or 2, please let me know. Okay, Sarvesh, in the first question, you have to calculate the relationship between work done by, okay, there are 3 frictionless slopes, A, B, or C. The work done by the block's weight. So now you know the formula that if your vertical coordinate is y and your horizontal coordinate is x, the work done by gravity is minus mg into delta y. Now if this height is h from here to here, then in each of the 3 cases, A, B, and C, in all these 3 parts, the vertical displacement is minus h. So in all 3 parts, the work done by gravity is the same. It is equal to mgh. That's one way to understand. Another way to understand is that the change in gravitational potential energy is negative of work done by gravity. So in all 3 cases, you can see that potential energy changes by the same amount in all 3. It changes by minus mgh. So the work done should be plus mgh. Should be plus of mgh in all 3 cases. So that is why the option C was correct. So this was a directly formula based question. Hope this was clear. So is the first question clear, Sarvesh? Okay. Let's move on to the second one then. So mass of the body is given to us. It is acted by on by a force like this. Due to the force, the mass is displaced from this position to this position. Okay, so initially the speed was so much. The final speed should approximately be how much? So work done by F should be equal to change in kinetic energy. Now work done by the force here will become dot product of force with displacement. So first of all, we need to find the displacement. Okay, so the particle is going from this point to this point. So the displacement vector will be this much in meters. Okay. So now you have this displacement vector and you have this force vector. You have to calculate their dot product. Okay, so as you can see, it will be 8 joules. That is the work done. So 8 joules should be the kinetic energy. Okay. Initially, the speed of the particle was 2 meters per second and its mass is 1. So half m into final speed square minus initial speed square is equal to 8 joules. Okay, that's what you get when you apply the work energy theorem. So 1 kg into whatever final speed square minus initial speed is given to us as 2 meters per second. That is equal to 8. Okay. So V final square minus 4 is equal to 16. Okay. So V final is becoming approximately root 20. So that is approximately, I mean, that's equal to root 5 to root 5. So now you have to give the answer approximately. So that will become the nearest one, which is approximate, is this. Okay, so this was also a direct application of work energy theorem. Now go through the third, fourth question. Let me know if anybody has a doubt in these questions. Okay, good. So let's move on to the next fifth and sixth question. Go through it, please. Let me know if there's any doubt. Okay, let's go through the fifth question then. Couple of people have asked the fifth question. So we have three equal masses or weights of 2 kg mass each. The tension in the string connecting B and C. So here you can see that this will be coming down, this side will be going up. So if we just a second, I'll zoom into this a bit. Yeah, so now we want to find the tension between this. Okay. So let's say this tension is T1, okay, and this tension here is T2. And the system's acceleration is E like this. So for the block E, we have the equation T2 minus mg is ma. And for the block B, we have the equation mg plus T1 minus T2 is equal to ma. And then finally for the block C, we have the equation mg minus T1 is equal to ma. Now we can add all these equations. So we'll get 2mg minus mg, T1, T1, T2, T2 will cancel out, is equal to 3 ma on this side. So as you can see, we'll get the acceleration as g by 3. And now we can substitute this acceleration back in this equation and we can find out the value of T1 as mg minus ma. So that will become 2 mg by 3 should become the answer. Now the mass of each one was given to us as 2 kg. So T1 should become 4g by 3. Okay, so this is how to work out this question. Is it clear, people? Okay. So let's move on. Sixth question, anyone has a doubt? I don't think so. It's pretty simple. Let's move on to seventh and eighth then. Okay, so eighth question, you have to again use the constraint relation. It is given to you that E is moving upwards with a velocity of 5 meters per second. You have to find B's velocity. So make use of that virtual power method which I have discussed with you. So first of all, you can see that if the tension in this string is T, then the tension in this string will have to be 2T. So on the block A, how much net tension is acting? 3T tension is acting. And E is moving up with 5 meters per second square. Or 5 meters per second is the velocity of E. So B will be moving down with some velocity if you want to find out. So on the block B, the tension acting is T. So we have the relation that 3T into VA minus T into VB should be 0. This is our constraint relation. So this is the method for calculating the velocity. Is the question clear, Sarvesh? Yeah, this is net power by tension. Net power, we can also think of it as net work done. Has to be 0 in the system. So in a very small time, this will have a displacement proportional to VA upwards. So the work done will be proportional to 3T into VA. Whereas this will have a displacement downwards, whereas tension is acting upwards. So this will have a work done proportional to minus T into VB. Now this total has to be 0. Okay. What about 9th and 10th question? Anyone has a doubt in these? Okay, so 10th question, you can see here that if you think of the free body diagram, you can see that this is having, B is having an acceleration like this. That means the spring force acting on B is like this. So if the spring force is inwards, that means the spring is extended. It must be in an extended state. Only then it can apply an inward force on B. So it must be applying an inward force on A also. So that means on A, the spring force is acting like this. So if this has an acceleration AB, then this must have an acceleration like this. Okay. So their masses are given to us. So kx is equal to ma into acceleration of A, and kx on the other side is also equal to mb into acceleration of B. Okay, but you can see here that acceleration of A is eastwards, acceleration of B is westwards. Okay, so now you just connect these two equations. So from this you can see that acceleration of A should be times acceleration of B. So 6 by 4 times 1.5. So 1.25, sorry, 2.25 meters per second square. This is the acceleration. Is it clear, Sarvesh? If anybody else is having doubts also, please let me know. So far only one or two people are asking doubts. So go through the questions carefully. Try to recall what you've done in the test. And let me know if there's any doubt. Anyway, is the 10th question clear, Sarvesh? Good. Okay, next go through 11th and 12th question. Let me know if there's any doubt. Okay, we'll go through 11th question. So just make sure you understand the question first, go through it. Okay, so in this question, we have to calculate the work done by this force. Now, this is what type of force? It is a constant force. Okay, so if we denote this as our x and y system, we can see that this force is F I cap, it's constant. Now, as the particle is going from this point to this point, first of all, this point should be A, should not be B. Okay. But anyway, as it's going from this point to this point, you can see that the displacement is this. This is the displacement. Even though it's going along the circular arc, this is the path of the particle. This is the path, but its displacement is this. So you can see that the displacement vector of the particle is how much? It is r I cap plus r j cap. Okay. So work done is going to be very simple. We'll just calculate by dot product. So that will become FR, dot product of this and this. So again, this is based on the definition of work done by constant force. So please make a note of this, people. Now what is happening? You are directly. Okay, let's move on to the next question. Anyone has a doubt in either of these three questions, 12, 13, or 14? Please let me know. Okay, Rahil. So we'll discuss 12th question and then 14th. Okay, so 5 kg block is thrown up a 30-degree incline at a speed of 6 meters per second. It is found to travel a distance of 2 meters before it gradually velocity comes to zero. Then the loss in mechanical energy due to friction. Okay. So to calculate the work done by friction. So what you have to understand here is that your block had an initial velocity of 6 meters per second on this inclined plane of 30 degrees. Okay. And its mass is 5 kg. Now, as it goes up, it decelerates and eventually it comes to rest. But after covering a distance of 2 meters. Okay, so distance or displacement, whatever, it's the same thing here. Okay. So you can also see that as it covers a displacement of 2 meters, the height through which it moves, that is going to be d sine theta. So 2 into sine 30. So it's going to be 1 meter. So it's going through a vertical height of 1 meter. Okay. Now, as it's going up, you can also understand that what are the forces acting on the body. There is mg. Okay. There is normal reaction. And there is going to be kinetic friction. So you can see that over here, work done by normal reaction will be zero because dot product of n dot s is zero. So if we apply work energy theorem, we can say that work done by friction is equal to change in kinetic energy plus change in gravitational potential energy. This is the total work done by friction. Is this statement clear, Rahil? Because we have work done by external plus work done by non-conservative force is equal to change in mechanical energy. Now, this is the work energy theorem equation. So from that we can write like this. Okay. So now you can see as you're going from here to here, the work done by friction is unknown. But the change in kinetic energy is final kinetic energy minus initial kinetic energy. So it is minus of 5 into 6 square. So that's how much? 18 into 5. No. So That's 90, minus 90 joules. That's the change in kinetic energy. Okay. And change in gravitational potential energy will be plus mgh, because it's climbing through a height of h. So your delta y is positive. So that's 5 kg into 10 into 1 meter. So that is plus 50 joules. So delta U gravitational is plus 50 joules. So now just substitute in this. So work done by friction is equal to minus 90 plus 50. So that is minus 40 joules. Okay. It's probably come to 41 because we have taken G as 9.8 as 10, but if you take G as 9.8, you will get 41 instead of 40. Okay, so hope the working of this is clear. Okay, so this is a good question for the direct application of work energy theorem. Yeah, friction is a mechanical force. We have discussed contact forces as mechanical forces. And anyway, it's asking that due to the work done by friction, what is the loss in mechanical energy? So you can see the work done in by friction is negative. So that is why we are seeing loss in mechanical energy is 40 joules or 41 joules. This is not the work done by friction. The work done is negative, but the loss in energy because of the work done by friction, that is positive. It's losing 41 joules of energy. Then 14th question, right? So I'm assuming 13th is clear to all of you. So coming to 14th question, now in 14th question, we will use this graph concept that see, we are given force versus S graph. Okay. Now we know work done in general is integration of FDS like this in 1D system. So in 1D system, F dot ds becomes FDS because everything is along one axis. So what is this? This is area under the graph. This is area under the force versus S graph. Okay. So at any point of time, if the displacement is so much, this area should be equal to integration of FDS. So that is nothing but work done. So just calculate the area. I will verify it for you. Just calculate it yourself once. Okay, so all of you just as a practice, calculate the area correctly and verify the answer. I'll put it up in a moment. Okay, let's finish the calculation with this. Yes, it's pretty easy. So you can see that this area will be half into base into height, okay, plus this area here will be base into height. So that is 2 into 10. So it's 25 plus 20 or 45 joules. So that should be the answer. Okay, so fairly straightforward question. All right, let's move on to the next set of questions. So question 15 and 16, just go through it carefully. Let me know if anybody has a doubt with these questions. Okay, question 15, let's go through it. So question 15 is a situation like this, that you have two springs. So from this you can see that if you take spring constant of B as K, then spring constant of A will become 2K. So you can think of this like 2K and this is SK. Now we are applying the same amount of force to stretch both the springs. Okay. So as a result of this force, if A is stretched by XA and B is stretched by XB, okay, then so we have F is equal to KAXA is equal to KBXB. So 2K times XA should be equal to K times XB. So XA is half of XB. The extension of A is half of the extension of B. Okay. Now it is given that energy of A is E. So energy stored in A is half Ka into XA square. So that is half of 2K into XA square, that is E. So energy stored in B, that will become how much? Half of K into XB we can write as XA by 2. Okay. So that we have to calculate. Okay. So you can see that UA is equal to KXA square and that is E. Whereas UB is becoming oh sorry, my mistake, this is double now. XB is double of XA. Okay. So this is becoming 2KXA square. So how much that is becoming? 2 times E. So your answer should be this 2E. Okay, Okay, so fairly straightforward question. Hope this is clear. Okay, let's move on. Sixteenth and 17th question, go through it. 16, 17, 18. Let me know if there's any doubt. Okay, we'll discuss 17th. Okay, Rahil, we'll go through 17th next. Okay, so let's understand in 17th question what is happening. Okay, as an object is dropped from a certain height, you can see that at a certain time, its speed will become gt and its displacement downwards, this downward displacement will become half gt square. Okay, so what is happening is that the kinetic energy is going to be proportional to t square. So you can see the relationship of kinetic energy versus time. It should be this type of a graph. It should be a graph of the type y is proportional to x square, because kinetic energy is proportional to t square. Should be that type of graph. Okay. Because on the other hand, the potential energy, it is initial potential energy, something, let's say, minus mgs, because it is coming down through a displacement of s. So it is some constant minus half gt square into mg. So it is some constant minus some constant into t square. This is the potential energy, how it's varying with time, where that constant is mg square by 2, like this. Okay, so how this graph will look like? This graph has to look like this. It has to have this kind of a shape. It has to be a parabola like this. It has to be like y is proportional to some constant minus x square type of function. So that kind of graph. So that is why this is the correct graph for potential energy, and this is the correct graph for kinetic energy. That is why this option is wrong, because here the potential energy is going like this. It should go like this. So B is the correct option. Yeah, Sarvesh, look at this diagram first. You'll understand from this. T equal to 0 पे speed 0 था तो kinetic energy कितना था? 0 था. So T equal to T पे kinetic energy कितना हो गया? Half mv square. Where V is what? GT. So your kinetic energy, how it is varying with time? It is varying according to this. You can see that kinetic energy is proportional to square of time. So it's a y equal to x square type of graph. So the kinetic energy has to be like this. So it has to be this. Whereas on the other hand, उसका displacement कैसे हो रहा है? Vertically downwards हो रहा है. So potential energy को क्या हो रहा है? It is decreasing with time. Delta U is is mg delta y na. Now here delta y is what? It is minus h na. It's coming down through it's minus half gt square. So that's why it's like this. So it's this type of graph. Okay, so hope this is clear. Okay, just make a note of this, then we will discuss question number 18 next. Rahil, hope this is clear to you also. Okay. Okay, let's move on to the next question. So the backside of a truck is open and a box of this much mass is placed on the trunk 4 meters away from the rear end. Coefficient of friction is given, G is given. The truck starts from rest with an acceleration of 2 meters per second square. So it's like this. Let's say this is the open end of the truck, open back of the truck. Now the truck which is going with an acceleration of 2 meters per second square. And on this we have placed a box which is at a distance of 4 meters from this. Okay. So what is happening is that in the frame of the truck, if you make the free body diagram of the box, in the non-inertial frame of the truck, so that non-inertial frame is moving with an acceleration a naught like this. So what is happening on this? There will be pseudo force acting like this. Okay, so that pseudo force will give it a tendency to slip. Okay. So you can see the pseudo force is equal to 20 kg multiplied by 2 meters per second square. So 40 newtons. Whereas normal reaction, which balances the weight, is equal to 200 newtons. Okay. Now we can see that maximum friction available is 0.15 into 200. So it is only 30 newtons. So maximum friction available is only 30 newtons. Okay. So here that means what is happening, that my pseudo force is greater than maximum friction available. So the block slips. Okay. And it slips that such that relative to this, it will have an acceleration E prime. Okay. So it slips with acceleration E prime relative to the truck or in the truck's frame. So that will be such that ma naught minus friction is equal to ma prime. So just now we saw that this is ma naught is 40 newtons, but the friction will be mu n. Okay. So just leave this way only. Yeah. So the pseudo force 40 newtons minus the kinetic friction 30 newtons is mass of the block 20 kg into acceleration E prime. So E prime is coming out to be how much? 10 by 20 or 0.5 meters per second square. So as a result of this, this will now slip off this at some time t. Okay. So after some time it will have slipped off. So in the ground frame it will look like this, that this truck has moved on and the box has reached here. But in the truck's frame it will look like the box has gone back by s. So half E prime t square should be equal to that relative displacement. So half into 0.5 into t square should be equal to this displacement of 4 meters. So from this you can see that t will come out to be 2 seconds, is it? Or 4 seconds? 4 seconds, sorry. So when the truck is at a distance of how much from the starting point, so the truck's displacement will become half into E naught into t square. Now we got this time as 4 seconds. So half into 2 into 4 square. So 16 meters. So 16 meters should be the answer. The displacement of the truck at that point of time. Yeah, you can solve in ground frame also, block over block. Yes. But then you'll have to use relative motion. That's why I'm saying pseudo force is a easier method of solving. Okay, so it is easier to solve this in the frame of the truck, okay, rather than to solve it in ground frame and then use relative motion. Unnecessarily, that will be a bit confusing. Okay. So anyhow, that's the 18th question. Hope this is clear. Now let's move on to last few questions. So go through the 19th and 20th question next, please. Let me know if there's any doubt. Okay, so let's look at question number 20 next. So a person pushes a 30 kg block through a displacement of 10 meters along a level floor, that means horizontal floor, at constant speed with a force directed at 45 degrees below horizontal. Coefficient of friction is given. Now in the 20th question, you have the same situation, but the force is applied. Okay, we have to calculate the work done by friction. So let's work out both 19th and 20. They are related to the same situation. Okay. So you'll see that if you can work out the 19th question, then the 20th is direct from that. Okay. So if this block of mass m is on a surface which has coefficient of friction mu, and now somebody is pushing it through with a force which is 45 degrees below the horizontal. So you're applying a force like this, such that this angle is 45 degrees. Okay, and you're moving it with a constant speed. So that means acceleration is zero. It's moving with a speed v, but at zero acceleration. Okay. And now the block displaces by a certain amount, s. So you have to calculate the work done by the force F and the work done by friction. So you start by making the free body diagram of the block with the forces resolved. So you can see that F's components will be F by root 2 like this and F by root 2 like this. The vertical and horizontal component, because the angle is 45 degrees. No. अरे friction है ना, so कैसे? Because it's a rough surface, na. So in spite of your this thing acceleration being zero, to keep it moving, you have to overcome friction, na? So there is kinetic friction, which is mu n. So unless you overcome that, the block will start decelerating, na? So understood the point. So the free body diagram is like this now. So acceleration is equal to zero means F by root 2 is equal to mu n. It's your first equation. And n is equal to mg plus F by root 2. That's your second equation. Okay. So now substitute this in the first equation and you'll get F by root 2 is equal to mu times mg plus F by root 2. Okay. So this equation you can solve further and you can write like this, that F by root 2 into 1 minus mu is equal to mu mg. So you get this relation that F is equal to root 2 times mu mg upon 1 minus mu. Okay. This is the formula for F that you get. And now you know m and mu and all this, so you can easily work out the value of this. Okay. 30 kg is the mass, coefficient of friction is 0.2. So you can work out. Okay, now you can see that as the block is moving like this, what is the work done by each of these forces? So let's look at that. Okay. So work done by F will be equal to Fs cos 45. So it will be F into S by root 2. So substitute this here. And work done by friction will be minus F into S. Now why I'm saying you can do this directly, you can also see that work done by F plus work done by friction will be zero, because the block is moving at constant speed. So change in kinetic energy is zero. Okay, and it's not changing in height, so its potential energy is also not changing. Okay, so you can see that work done by friction is actually negative of work done by F. Okay, so that's how you can do this directly. Okay, Now see, in the first part, you have to calculate the work done by F in 10 meters. No? So that will become root 2 into mu mg. So that is 0.2 into 300 newtons divided by 1 minus mu. So that is 0.8. Okay. Into S, which is 10 meters, into 1 by root 2. This whole factor. This. Okay. So this is becoming how much now? This is becoming 300 by 4. That's 75. So it's becoming plus 750 joules. Okay. Work done by F is 750 joules. So this is your answer. And the second part in this, you have to calculate the work done by friction for the same displacement of 10 meters. So you don't need to sit and calculate this again. You can just use this concept. So the work done by friction for the 10-meter displacement has to be minus 750 joules, because the net work done has to be 0. So that's why I said that you can do this question directly making use of the 19th question. Hope this is clear, people. Just go through it carefully. Okay, so hope the calculation part is clear. Just do the calculation yourself once and make sure you're able to understand how we got 750 joules here and minus 750 joules for the work done by friction. Okay, so is the calculation clear, people? Anyone has a doubt, please let me know. Okay. So let's come to the final couple of questions. I think these are pretty simple questions, so let me know if there's any doubt. Okay, 11th one, let's discuss. So we are going through the 11th question. It says the block of mass m is hanging over a smooth and light pulley, the light thread. The other end of the string is pulled with a constant force F. Okay, so this is very similar to the last question actually. Kinetic energy of the block increases by 20 joule in 1 second. Okay, so we have this kind of a situation. So the other end of the string is pulled with a constant force F. So whatever that constant force, that will become the tension in the string. So T is equal to F. Now, okay. So now let us assume that okay, this block moves from here to here. This is the displacement in 1 second. So the kinetic energy of the block increases. So going from here to here, you can see from position A to B, the work done by the tension on the block should be equal to the change in kinetic energy plus change in gravitational potential energy. So this will be the same thing as T into S. Okay, so that should be equal to change in kinetic energy plus mgs because it's increasing in height. Okay, so this quantity now is given to us as 20 joules. Okay, and this is mg into 1 meter. So wait, tension in the string definitely has to be, so if it's going up and kinetic energy is increasing, you can see that speed is increasing. So you can see, so let's go option wise also. So you can see that since kinetic energy is increasing, therefore speed is increasing. That means the acceleration is not zero. So if you think of the free body diagram of the block, it is accelerating upwards. So that means T is greater than mg, and T is the same thing as F. Okay, so we can see that the tension in the string is mg will be a wrong option. Okay, the tension in the string is F, and that F is greater than mg. So that is the thing. Okay, now the work done by the tension on the block is 20 joules in 1 second. That is wrong, because the work done by the tension is equal to the change in kinetic energy plus the change in gravitational potential energy. So that is why this option is wrong. Okay, and work done by gravity is this much. That's also wrong, because work done by gravity is this. So work done by tension plus work done by gravity, the sum of these two is equal to 20 joules. This is the correct statement. Okay, the sum of work done by gravity plus work done by tension, that is 20 joules. So that's why option C and D are wrong. Now, because the mass and all is not given, so we cannot calculate anything else over here. Okay, so we will leave out this calculation part, but we can just understand logically by application of work energy theorem that option C and D are wrong. So this is a little bit more tricky type of question, because when you look at the question, you might think that, okay, if they've not given the mass, then how we can calculate? But we can rule out the options by just, understanding that how much the work done is we can't calculate, but we know definitely it has to be less than 20 joules, because the sum of these two things is 20 joules. So each one of them cannot be 20 joules. Is it clear, Sarvesh? This was a bit of a tricky question in that sense. वो तो string का property है ना बेटा. At the other end of the string, if you look at the free body diagram of this point ना, it's a massless point, so tension must be balanced by F, and it's a massless thread, so tension is uniform everywhere. Okay. Now, how we know the block is accelerating? Why T is not equal to mg? Because we are given that kinetic energy is increasing. Agar F had been equal to mg or tension had been equal to mg, then the kinetic energy would not have increased. Okay, so hope it is clear now. Right, so that completes this question, and that completes the discussion of the paper. Yeah, there should be no motion, or there can be a situation, Sarvesh, where it's moving up but with constant velocity. If T was equal to F, it can also be moving up or down with constant velocity. But constant velocity means the kinetic energy should not change. So there can be displacement of 1 meter, but it cannot be such that, you know, there is a change in kinetic energy. So that's why. Anyhow, so that completes this discussion of the paper. Now let's get back to our discussion of work energy. So we are more or less done with the concept set of work energy, but few additional things and bit of practice of questions we will discuss. Okay, so work, power, energy. We have to also discuss about power in detail. So we have been discussing about work energy theorem. That is, for any system, the work done by external forces plus work done by non-conservative forces equals the change in kinetic energy plus the change in gravitational potential energy. Sorry, the change in potential energy in general. Okay, whatever type of potential energy the system has. So this is the statement of the work energy theorem. And we also saw that for an isolated system, if the work done by external forces and the work done by non-conservative forces is zero, then it's called an isolated system. So in such a system, the change in kinetic energy plus the change in potential energy is zero. That means the sum of kinetic energy plus potential energy is conserved. So the sum of kinetic and potential is called mechanical energy. So for such a system, an isolated system, what happens is that the mechanical energy is conserved. So this is the general application of work energy theorem. So let us start with an example like this today, that if the kinetic energy of a block increases by 20 joules and its potential energy decreases by 20 joules during the same period, then which of the following is correct? Work done by external force must be zero. Work done by non-conservative forces must be 0. Net work done by external and non-conservative forces must be 0. And again, net work done by external and non-conservative forces is equal to plus 20 joules. Now quickly go through the options and tell me which of these is correct. Yeah, so please send me the text message indicating which answer is correct here. See, from this and this given in the question, you can understand that the change in kinetic energy is plus 20 joules. The change in potential energy is minus 20 joules because it's saying the potential energy is decreasing by this. Okay. So now when you apply the work energy theorem, you can see the statement that external force work done plus work done by non-conservative forces is equal to change in kinetic energy plus change in potential energy. So the only thing we can say for sure here is that this quantity is equal to 0. So the only aspect we can be sure about is that the net work done by external forces plus non-conservative force must be 0. So that's why only option C is correct. Option D is definitely wrong, and option A and B may be correct, may not be correct. Okay, so because it may be that individually both these quantities are 0, but it may also be that work done by external is some positive quantity and non-conservative is some negative quantity, such that their resultant is 0. Okay, so let us look at the application of this kind of concept in a numerical problem. Now, suppose we have a situation like this. Okay, so we have a path which is like this. This section is rough. It has some coefficient of friction mu, whereas this section is smooth. Now, a particle is released from some point over here. Such that it is at a height h equal to 20 meters. So a particle is released from the point C with initial velocity 0 at a height with respect to the rough horizontal section AB. So the particle slides down the smooth curve CA and then slides through a distance of 100 meters from A on the horizontal part AB before coming to rest, before finally coming to rest. So first of all, find its speed at the point E. Secondly, find the coefficient of friction mu. How much is the coefficient of friction on the rough surface? Please, please let me know the answer of both the parts. Yes, that's correct. 20 meters per second is the answer for the first part. And what about the second part, coefficient of friction? So you can see that as the block comes sliding down from C to A, if we apply work energy theorem, we will get change in kinetic energy plus change in gravitational potential energy is zero, because there is no friction. Okay, and no work done by external force either. So no friction means work done by non-conservative force is zero, and there's no external force doing work either. So plus half mva square minus mgh should be zero. So very simple, va should be root 2 gh. So it is 20 meters per second. Now suppose it stops somewhere here. This point, its speed becomes zero. So let's say this point is d. Now this distance is given to us as, how much is it now? 100 meters. Okay. So this distance is 100 meters. So next you apply work energy from A to D and you calculate the coefficient of friction from that. Yes, that's correct, right? Anybody else got the value of mu? Okay, so let's go through this section. So mu should be coming out to be 0.2, and let's understand how. So as the block is going, or as the particle, whatever, is going from on the rough surface from the point E, where its speed is given to us, we know it's 20 meters per second, to this point here, where its speed is becoming zero. Now, at any in between point, the forces acting on it are weight, normal reaction, and kinetic friction. So that kinetic friction will be equal to mu n equal to mu mg in magnitude. So you can see that the work done by friction from A to D, this point A to this point D, the work done by friction will be minus mu mg into the distance. Okay, and E to D, what is happening? The work done by the friction will be equal to the loss in kinetic energy, because delta U is anyway zero. So minus mu mg into S is going to be minus half mva square, because the final velocity is zero. So from this we'll get the coefficient of friction as va square by 2 gs, like this. So 20 square by 2 into 10 into the distance which is given to us, 100 meters. So mu will come out to be 0.2. This is the work energy way of solving it. You can also do it by using kinematics. You can also do it this way, that you can find out that the deceleration will be kinetic friction by mass, so mu g. Now you can use the relation that v square is equal to u square minus 2as. So 0 is equal to 20 square minus 2 mu g into s is 100. So from this also you can see mu will come out to be 0.2. So hope this is clear to all of you. Fairly straightforward application of work energy. Okay, next up, we will understand the concept of power. Okay, so definition wise, power is defined as power delivered by a force equals to the rate of work done by the force with respect to time. So in other words, according to this definition, we can define instantaneous power P delivered by a force F. So this instantaneous power will be instantaneous rate of work done, like this. Okay, so this is equal to instantaneous rate of work done with respect to time. Okay, so in this formula you can see that this becomes F dot ds by dt, because in a small time dt the work done is F dot ds in time dt. Okay, so the power which is dw by dt can also be defined like this. Okay, or let's write this in reverse order. So the power which we are defining as work done upon time, but instantaneous work done, so that is F dot ds divided by that very small interval of time. Okay, now we know that ds by dt is nothing but the instantaneous velocity. Okay, so instantaneous power delivered by the force also gets defined as F dot ds by dt, so that becomes F dot b. So now this becomes something very important for us. The definition of instantaneous power, which is instantaneous rate of work done, can also be simply calculated as the scalar product of force with velocity. Okay, so this rate of work done can also be calculated as the scalar product or dot product of instantaneous force and instantaneous velocity. Okay, so just make a note of this and we'll discuss more about this next. Yes, F is the force at the instant of time between t and t plus dt, and v is the instantaneous velocity of the body on which the force is acting. Okay. Now we also define something called average power. So this average power is equal to the average rate of work done with respect to time. So average power becomes total work done upon total time, or it becomes fine. So write down both these things together. Instantaneous power is instantaneous rate of work done. Average power is average rate of work done. Just like you make the definition of velocity in terms of instantaneous velocity is instantaneous rate of displacement with respect to time. Average velocity is average rate of change of velocity with respect to time. So just like these two separate definitions for instantaneous and average, like that you have two separate definitions for instantaneous power and average power. Both are in terms of rate of change, but one is instantaneous rate of change, so you use differentiation for that, and the other is average rate of change, so you use total work done upon total time. Okay, now next thing we'll understand is the unit of power. So hope you are done writing this down, Varun. So power is measured in watts. Okay. So the unit of power is, the SI unit is watts. Named after the physicist James Watt. So 1 watt equals to 1 joule per second, which is the same thing as 1 Newton meter per second. CGS unit is, there's no separate name for it, but it is erg per second. Okay, and 1 erg per second is the same thing as 1 centimeter per second. So you can see the conversion between these two is 1 watt, which is 1 joule per second, is 10 raised power 7 erg per second. So this is a conversion between CGS and SI. Now, one more factual thing you should know, which is not really important from syllabus point of view, but also in the old British system of units, you had something called horsepower. Okay. Or sometimes it is also called British horsepower. BHP. So this unit is still used in automobile industry. So 1 British horsepower is approximately 746 watts. So we will not be using this, but in automobile industry, you see that the power of an engine, the maximum power an engine can deliver, is expressed in British horsepowers or horsepowers. So just a factual thing for you to know. Okay, so let's look at very basic question to start with. So what we're doing is we're looking at a projectile fired from the ground level. So at t equal to 0, a projectile is fired at a speed of 50 meters per second at an angle of 53 degrees with respect to the horizontal. And the acceleration due to gravity is 10 meters per second square. So we have to find out the instantaneous power delivered by the weight mg of the particle. Okay. So it has a mass m, which is also given to us. Suppose the mass is 2 kg at t equal to 0. Then again equal to 1 second. Then at the instant it reaches the maximum height from the ground. Okay. Then again at t equal to 5 seconds. So this is the first part. And second part, we have to also calculate the average power delivered by the weight from t equal to 0 to t equal to 4 seconds. So in the interval of 0 to 4 seconds, what is the average power delivered by mg? So this is a typical type of question to do with calculation of power. So we'll just apply the definition of instantaneous power by a force as F dot V, and we'll apply the definition of average power as total work done upon total time. Okay. So just work this out quickly using this definition now. The rest of it is just about applying kinematics. Okay, so this is a fairly simple question. All you have to do is understand how to write the velocity and the force in XY component system. So you can see that in general in projectile motion, what happens is that if your velocity is Vx I cap plus Vy j cap at some time t, okay, then Vx is equal to Ux is equal to u cos theta, which in this case is 30 meters per second, but Vy is equal to Uy minus gt, which in this case is 40 minus 10t in meters per second. So now just use these formulae. Okay, so at t equal to 0, you can see that the initial velocity in component form is 30 I cap plus 40 j cap, and the gravitational force is minus 20 j cap in newtons, because the mass is 2 kg and g is 10 meters per second square. So power delivered by mg is going to be mg dot velocity. So you can see it is minus 800 watts. And just the dot product of these two you have to calculate. So this is the A part for the first question. Now similarly at t equal to 1 second, you can see that the velocity will become 30 I cap plus 30 j cap. Just substitute t as 1 second in this. You will see the vertical component has reduced to 30 meters per second. So now the new power delivered is going to be minus 20 j cap dot product with 30. So it's going to be minus 600 joules. Sorry, watts. Okay. Now likewise, when it reaches the highest point, at highest point, the velocity just becomes this. Okay. So power delivered by mg will become 0, because the vertical component of velocity becomes 0. So velocity becomes perpendicular to the gravitational force at the highest point. So hope it is clear so far. And now using the same method, work out the D part yourself. At t equal to 5 seconds, the first thing you do is you find out how much the velocity is. And then you calculate the power by calculating this dot product. With whatever velocity you get over here. Okay, so if you calculate this velocity using this formula here, you'll see that at 5 seconds, Vy will become minus 10. So your velocity will become 30 I cap minus 10 j cap in meters per second. Okay, so this dot product will now result in a positive quantity plus 200 watts, because what is happening is that at 5 seconds the projectile will be on its way down. The projectile will be somewhere here at 5 seconds. So its velocity will be like this, whereas the gravitational force is like this. So you can see the dot product will be positive. Whereas, for example, at t equal to 1 second, or somewhere over here like this, so the velocity and gravitational force were at an obtuse angle. So the power was negative. At the highest point, the velocity was perpendicular to the gravitational force. So the power was 0. Okay. So anyway, that is this part. Now coming to the second part, the average power. Average power from 0 to 4 seconds. Let's calculate that. So the average power is going to be work done by mg divided by the time interval. So we have to calculate work done by mg from 0 to 4 seconds. So work done by mg, remember, is minus mg delta y. So we have to find the y coordinate of the projectile. Now the y coordinate of the projectile is u sine theta t minus half gt square. So you can see that y at 0 was 0, whereas y coordinate at 4 seconds will become like this. Because u sine theta was 40. So this will become 40 into 4, that's 160, minus 5 into 16. So that is 80. So it's 80 meters. So the y component of displacement is 80 meters. So this work done by gravity part will become minus of this much. So minus of 1600 joules. This is the work done by mg. So the average power will be minus 1600 joules divided by the time of 4 seconds. So the average power is minus 400 watts from 0 to 4 seconds. Okay, so this is an example of the calculation of average power as the total work done divided by total time, where of course we've used the direct formula for work done by gravity, which we understood from the dot product method earlier. Okay, so make sure you understand this concept of power and average power when you revise today's lecture. And next time we'll see some more questions based on this, and also some more tricky type of questions in work energy theorem application. But now we are done with the concepts of work energy. So please go ahead and complete your module questions and questions from DC Pandey or whatever book you're using for your NEET reference, NEET physics reference. Okay. Next chapter we'll be doing after this will be instantaneous velocity survey, which is coming from the formula of projectile motion. If you just revise the concept of projectile motion, in that you know how to find the formula of velocity as a function of time. Projectile motion you have studied in kinematics. But a projectile motion, this is straight line motion. Projectile motion you've done in kinematics, no? The first part of kinematics. Yeah, that you have to use. So x component of velocity is constant, u cos theta. Y component of velocity is u sin theta minus gt. To divide the motion into components, and that's how. Okay, so that's it for today's session, people. Wish you all the best.